think you'll really enjoy the talk today. So I'll just preface it by saying that the idea of missions to Mars have been around since Mars captured the human imagination roughly in the 19th century, when this idea, somewhat mistaken, that there were canals on Mars arose and people imagined that it was actually inhabited. But this gave rise to all sorts of literature about life on Mars, and also the question of actual missions to Mars. And now the idea of a mission to Mars has really gained some currency. But in order to realize that, there are a lot of technical challenges that have to be overcome. One has to worry about ionizing radiation, the very long trip to Mars and how humans would actually make it in that, and then a very long stay on Mars and extensive exploration that would entail. So there are multiple engineering challenges that have to be conquered in order to make that a reality. So it's my pleasure to introduce Dava today, who is going to speak to one of those particular challenges, which is actually how to enable human exploration on the surface of Mars with these smart suits. She is a professor of aeronautics, astronautics, and engineering at MIT, and also a director of the MIT Institute or Program for Technology and Public Policy. She specializes, as you might guess from the talk and the suit, in multidisciplinary approaches to aerospace and bioengineering, and a number of other topics that touch on those. Her current focus, as you might imagine, is on advanced spacesuit design, but also mission analysis and public policy analysis. In addition to these interests, she has an ongoing interest in ways of aiding human locomotion, and that would be specifically on Earth for people who might be challenged by that. She did her undergraduate work at Notre Dame and got her doctorate at MIT in aeronautics, biomedicine, and engineering, and is the author of a book on interactive aerospace engineering design. And if nothing, Dava is resourceful, so I'll just give you one quick illustration of that. She did a circumnavigation of the globe in a sailboat, and when she was sailing west out of Panama towards the Marquesas, she developed a leak in the hydraulic system for the steering mechanism in her vessel. And the next morning, undaunted, she figured out first how to fix the leak, but then what do you do for hydraulic steering fluid? So she realized she had taken on board a fairly large amount of extra virgin olive oil, and then managed to jury-rig the system to make the steering mechanism work, and made it successfully to the Marquesas, where she could get a full repair and the proper hydraulic fluid. But it turns out extra virgin olive oil has the right viscosity to match the hydraulic fluid in a steering mechanism. So if you ever need this, you can thank Dava for that gem of information.
Thank you very much. It's a pleasure to be here. So delighted to be here. Everyone can hear me? Excellent. So I'd like to take you on a journey. We'll go from Earth to Mars. I'll talk to you about some of our suit development. And of course, my passion is exploration via space or sea. So I am focused on sending humans and robots back to the moon, perhaps, and onward to Mars. But I'd like to start first with an image and give Buckminster Fuller, the top left there. Bucky Fuller had an idea of mini Earth. And what if we were, the United Nations building, and all of the world leaders would look out the window and envision the Earth? It's, of course, a pretty radical idea for his time. Now we could realize it, of course, with technology. We can put, a wonderful image, physical, but with all of the world's weather, wars, famine, happiness, celebration, so that maybe we could really envision that. So in all of our space research, it really pretty much tells us about ourselves and what, our humanity, and we always kind of reflect back on Earth. As an aerospace engineer, I try to have dual use applications for some of our inventions. Again, we're not going to send too many people to Mars in the future, maybe a few lucky ones. Hopefully they'll be my students in the future. But most of our ideas and designs can be used here on Earth as well. So I'll share the story of some of our suits. As my partner in crime there, Guy Trotty, on that image, and he was, the two of us are the ones who sailed around the world. So let me tell you just a little bit about what happens when we go into space. Long duration space flight is what I'll be talking about. So you're going to lose 30% muscle atrophy. And here, look at that's just kind of noise from the lab, actually. This is human-powered artificial gravity. Artificial gravity meaning short arm centrifugation. So that is myself a long time ago with one of my students, but I like to give credit. The great design project, student project, I always hop on the devices first, just if we do have human use approval. I know this is being recorded. We get human use approval, and then we get to do the human studies. But how are we gonna, get to Mars? Maybe conventional propulsion, but if and when we do get to Mars, how are we going to keep our astronauts healthy? That's what most of my research focuses on, the musculoskeletal integrity, and then as well as suit design. So you're going to lose 30% of muscle atrophy. You're going to lose about 40% of your muscle strength, but that's the good news. The bad news is you're going to lose your skeletal integrity, namely bone mineral density, at the rate of 1 to 2% per month. So now how many people want to go on my 6 months to space station? No, come on, I get more volunteers than MIT. Come on, you guys. All right, so now, because that's the easy question. How many want to go on a 4-year Mars mission? That's where the hands are supposed to, come down. So we have challenges. That's great. That's great news for us because that's just a challenge. And then, again, back to artificial gravity. So we'll throw everything at it. We'll throw exercise. We'll throw pharmaceuticals. Maybe some interesting suit design, and then artificial gravity or short arm centrifugation. That's another specialty of our lab. Spinning people up, you don't get too sick, and we can recreate 1G. Of course, it's just acceleration, 1G at your feet to, again, try to keep you healthy and well. Okay, so that's a quick intro to the challenges that we have. Show you a few of the other things that we look at in the lab. Play a few more videos here. There we go. So if you come to the lab, this is what I call the moonwalker, and that's just my great graduate students running at 1G, of course, getting warmed up. Okay, so now here's what happens when we do a Martian simulation. So this is 3-ACE-G, or 3-ACE your body weight. Looks pretty comfy, right? That's a lope, actually, when you break down the biomechanics. There's a little force plates there. Okay, and then, we don't have too many spacesuits to go around, so we devise these contraptions. That's my cheap spacesuits run about $20 million a copy. But my exoskeleton here, those are stiff legs. And get on a treadmill, get on that little moonwalker. Now we're talking, and I'm measuring all the energetics. What are your energetics? And it turns out you lope, and again, these kind of low gravity simulations. And so we do biomechanics, we do energetic analysis, and we're trying to figure out how people are going to perform. Some of the other simulations that we can do, let's see here. Go underwater, because underwater is another place. This is an instrumented treadmill, but it's underwater for a lunar condition. That's 1/6 your body weight. So through the center of mass of the limbs, he was loaded for 1/6 mass. And here's a 3/8. This is Mars. So again, that's kind of loping, but you're a biped, right? You're bipedal, nice airtime. I always wished I could slam dunk, so you can do it. Now here we are flying on NASA's aircraft. So this is truly lunar gravity. This is the only way on Earth I can get lunar gravity. And here comes a Martian gravity. So we're flying parabolas. And so I haven't been to Mars, but we've definitely flown thousands of parabolas in lunar, Martian, and zero gravity, the weightless condition. It's also known as the vomit comet, but it's a small price to pay. So you go up about 40,000 feet and you drop like a rock. And so you get this great 20-25 seconds over the top. It's a nice Keplerian trajectory. And you're weightless. It's really cool to be weightless. All your organs float. I think that's what you notice first. Like you're floating, but everything floats. And you don't have very much control at all. So, and so we study that. Adaptation to very extreme environments. So Moon, Mars, microgravity, those are my extreme environments. This is a blue suit that you see here. Actually, these one-handed push-ups, I don't recommend those on Earth, but those are great to do on the NASA aircraft. And so we're always measuring forces and torques and trying to quantify motion and see how people are performing. This is called our gravity loading countermeasure suit, and I'd like to tell you a little bit more about that one. We're testing it, designing and developing it, and it's an exercise countermeasure suit. And Here's some great postdoc and graduate students in it. And Richard Owit, he's a space tourist. I think he paid about 30 million to go up with the Russians. So I guess, if you want to do that, it'll get cheaper. Just stay tuned. But what are we doing? Why do we have all these blue suits? Well, again, it's for inside the vehicle. Okay, we call it a gravity loading countermeasure suit. So basically, if you're always moving, I told you about the musculoskeletal loss. So if you're always moving as you go around, we can just put some resistance, a little bit of resistance. Imagine it like a bungee suit. You're kind of working out against a bungee suit. I don't have it in the arms because your arms don't lose musculoskeletal integrity, but longitudinally. We have a real problem with the spine, we have a real problem with the legs. So we load through this spandex suit the musculoskeletal system. And then we test it out in the environments. So it will fly with the European Space Agency. They like our technology, that's good. So it'll fly to ISS in 2015. So we have some parabolas coming up in spring 2014, and then we'll give a Danish astronaut a nice blue suit, and Andreas will fly, and then hopefully we'll continue perhaps with another international station flight as well. Okay, well, back down to Earth, the blue suit, if you will, has really important Earth applications that I'm interested in. So kind of a typical gate lab, we have a lot of cameras, we watch people go up and down stairs, and we're trying to, we always tilt surfaces on them because, again, extreme environments. What I'm showing here is actually some IMUs. These are inertial measurement units. They're little sensors, but the great thing is that in a high-end motion capture lab, that's about $200,000. A person can, only go from here to there. Well, we're trying to replace that by orders of magnitude with these little sensors. Basically, strap them on and get these are kinematics. The data that you're seeing is a knee angle over time, and the green is the high-end, let's say, gold standard kinematic tracking system, tracking angles, motions, and then the blue are our IMU measurements. So we're right there. We can use, very cheap, inexpensive systems, hundreds of dollars, to try to get the information that we want. And particularly what we're looking at, and this is in collaboration with some Russian colleagues, because this fellow that you're looking at here, this little guy, he's wearing something called an Adeli suit, and that is a commercially available suit. It comes off of what's called the Russian penguin suit. All the cosmonauts, when they're on space station, they wear the Russian penguin suit. It's kind of the counter to our blue suit. But if you make a little version of it, and literally like to show this because you do have these little surgical tubing straps, if you will. It is a little bungee suit, and this little fellow has cerebral palsy, and so he's strapped into the suit, and you're trying to increase some muscle and motor control and muscle tone and things like that, just to help him improve on some of his just daily life activities. So we think that that's really promising, so we're still collaborating. The issue with this isn't very comfortable, and it's what we call a two-stage suit. There's a lot of loading here, and there's some loading here. We think that if you have loading, very small amounts of loading from the shoulders to the feet, it's a much more comfortable suit. And so that's what we're playing around with, the material properties and the forces that I can create to make a nice, comfortable suit. But we think that that's a pretty wonderful application. So we'll continue working on that for the next 5 or 10 years and see if we can't make some improvements. Okay, so now that blue suit, if you will, was for inside the vehicle, IVA, intravehicular activity. Well, it's even more of a challenge to send the astronauts outside the vehicle. So that's what we call EVA, or extravehicular activity. So in terms of engineering, this is it. We have the world's finest spacecraft. It's the smallest spacecraft. It's an unbelievable engineering feat. It's beautiful, totally self-contained. You have to pressurize the person. You have to protect them from extreme environment, meaning hazards and thermal. There's not much radiation protection in a suit. It's better to do that in your spacecraft because it gets massive and dense and heavy. And we worry a lot about human performance. Again, that's kind of our specialty, mobility. Gloves, the Apollo astronauts have all been interviewed extensively. We've done some of that. And so if you're going to change one thing about the suit, change the glove. Those gloves, they were beat up. Today, currently, there's a lot of injuries in the suit. I'm going to talk about that as we continue on, but you might not know it because we still don't talk about it, but there's a lot of injuries happening because you're in a gas pressurized shell. It's about 140 kilos. We're approaching 300 pounds if you speak in English units, right? It's a heavy suit. Microgravity, it doesn't matter, but this is not going to work for Moon and Mars. So it's a very heavy system. You're gas pressurized, so it's very immobile. But again, give credit where credit's due. The backpack on the back, call that the PLIS, for a portable life support system. And again, oxygen, scrubbing your carbon dioxide, providing all of your control systems, making you comfortable. You don't get much to eat. Little food bar, little drink bag. That's it. So here's I just like to show this. This is what I call my Apollo bloopers. There's sound. I won't turn on. That's Jack Schmitt, the first geologist we sent to Apollo 17. He really wanted to do science. And this is his instrument, and that's his logbook. This one goes on. And 1960s, early 1970s, this was fantastic. That's a great suit. But again, it didn't enable the mobility and the scientific exploration that we'd like him to do, especially today. As an engineer, it'll be an insult if we don't go back to the moon with something much better in terms of capability. So this is the current state, the current NASA suit. We flew it on shuttle, and now we still fly it to International Space Station. So it's had a good long life, decades. It's called the Extravehicular Mobility Unit, or EMU. And we kind of envision in my lab, kind of a different future. I'm going to shrink wrap the astronauts, but a little bit more about the current state of the art. I think I've mentioned these numbers to you. It's pressurized to 1/3 of an atmosphere. That's all you need physiologically to keep someone alive in the vacuum. So that's great because you don't have to pressurize it to 1 atmosphere. We kind of take this 1 atmosphere for granted that we're sitting and talking in right now. But I have to provide 1/3 of an atmosphere to keep you alive. And like I said, it's not a locomotion suit. It was never designed to be a locomotion suit. It was designed, to be for shuttle or station. So this is just a little bit of the research that some of the designs that we're working on are, again, mobility, make it much lighter weight. We have a safety increase I might mention, but some of our current research now is, can we make it tunable in terms of the stiffness and things like that? Well, this is called the BioSuit. We'll talk about that. But in the lab, if you come to the lab, well, once in a while I get a suit there, but I have this nice robot. It's actually a little bit older technology nowadays. It's called MTAL Chief. That's a quiz question. If anyone knows why. Because NASA calls it the robotic spacesuit tester, and I just got tired of saying RSST. So my robot's called MTAL Chief, and in honor of Maria Tall Chief, of course, amazing ballet dancer and founder of the New York Ballet Company. So we have angles, you move around, we track you with motion capture, we put those are called kinematics, put those angles into the robot. Now the robot dances just like you were dancing. And the great thing about the robot is it has high precision sensors, so I can see what the torque is towards how hard are you working. And if I'm moving like this, maybe I'm not working too hard, I put a suit on you, you're going to be working really hard. Matter of fact, you're going to waste about 75% of your energy just to move your limbs. That's not good. I want you to go find life on Mars. So I don't want all your energy to be going against this gas pressurized suit. So and here's a little bit of data. This is just a torque, elbow flexion torque versus angle. Again, you're always working against the current suit. I told you that the suits cause a lot of injuries. Matter of fact, we've had over 26 astronauts now having to have major shoulder surgery as a result of injuries sustained from wearing the current spacesuit. They're pretty recent injuries. They're training injuries. You're training, you're going to have the world's largest swimming pool at NASA, a 6.2 million gallon tank, 33 million liters, if I did the math right. Anyhow, it's huge. It's enormous. You can put a whole model of space station in there. I mean, it's fantastic. But train. We train about 11 hours underwater for each on-orbit EVA hour. And we used to train inverted, meaning you're upside down because you can float around space, but we don't get rid of gravity here on Earth. So now you're inverted. These suits have really hard psi bearings, just fancy word for shoulder bearings. We call them psi bearings. So now, guess what? Your clavicle, some nice small musculatures there. You're moving, you're trying to do really intense repairs, like fix the Hubble telescope. So another reason, so this project we're actually putting, it's actually a suit within a suit. We're working on, can we protect, because again, at the cost and investment in the current suit, we have to think about how can we protect the astronauts and still use the current suit. So just a lot of our nice images and schematics, but we're studying this quite hard, and I wanted to put these slides here to show you, because this is a really wonderful collaboration that we have with with Harvard. This is our work, but this really great sensor, this nice small pressure sensor comes out of Rob Wood's lab here in the Wyss Center at Harvard. So it's really great. We're collaborating using these sensors and tell you a little bit more about the technology. But again, using these, so we embed high pressure sensors. This is actually a commercial project with, again, these sensors that we've worked on in collaboration, and then we've embedded them into a new suit. It's a shirt, it's a garment. And so we're measuring basically the hot spots, the pressure profile. We don't know how the human's moving within the suit. So now, well, I guess next week, the week after Thanksgiving, we'll be down in NASA Johnson Space Center and take our first spacesuit measurements, this kind of suit within a suit, to map this out, map out those hot spots, and then again, the next year of that work will be to put padding and protection so that the crew are not sustaining these injuries that need surgery during their training hours. So that's a fun suit. Moving on to what we call the BioSuit. That's definitely kind of bio-inspired. It's a different idea. It's different technology. So rather than a gas pressurized shell that you have to work against, so there's only one other way I can think of to apply pressure, and that's directly to the skin. Now, we didn't invent this. Dr. Paul Webb thought of this in the very early 1970s, and he had the idea, came up with something called the Space Activity Suit. Hold on to that thought. I'll show you a picture of it. But I think it was just maybe a great idea before its time. So it's called mechanical counterpressure, or MCP. It can provide you great mobility, flexibility. It's very lightweight. And these kind of armadillo looking like shells at the back of the suit actually has that, because I still need to provide you oxygen and scrub your carbon dioxide. So we need a bit of a frame in the back. But if you model nature and look into nature, I can give you a pretty nice articulating back plate that you can probably carry your nice little modular oxygen around on. So everybody gets their own suit. It's custom fit. And you can pick your own color. And then again, we're using our designs and technologies in the hopes of some pathology here on Earth. So that's kind of the big picture. I'll show you a little bit of history. This is Dr. Webb's suit, the space activity suit. So he did realize a mock-up. Again, this is a pretty fantastic 1971. He had his test subject, it was demonstrated for NASA. It's hard to see from this old film, but he does have a gas pressurized helmet. And he doesn't have a backpack on because he's getting there. But, again, showing great flexibility and mobility, but he didn't have the benefit of huge material science and breakthroughs that we have today. That's why this is really important. So, and you also don't have your two buddies with you on Mars to dress you. That was a big downside. So this is called the donning and doffing, putting it on, taking it off. We have a donning, doffing problem here. But we have, very tight-fitting skin suit, if you will, a pressure bladder, not much different than you'd use for high-end kind of commercial diving operations, a nice pressure bladder. And anyhow, NASA reviewed this. The soundtrack on this is very funny. You see the NASA spacesuit reviewers are saying, that looks like a leotard for a 2-year-old. And the subject's a little bit bored, but they eventually squeeze him in. They're squeezing, still squeezing. This is a 6-layer mechanical counterpressure system. And so it was flexible, but again, you couldn't put it on and off. We have a goal of about 10 minutes to dress yourself, put the suit on and take it off. That's very necessary. Here's some gloves going on. Same thing, kind of like shrink wrapping gloves. But I like that. There's an infographic in the back here. It's just part of a poster for the folks in the front. Anyhow, this is every mission that's ever flown, both NASA and Russia. And the little dots are the numbers of spacewalks we've done, numbers of extravehicular activity. So, we got started and we did a few in Gemini, and we went to Apollo, and the Russians did a few in Salyut. And we keep building up, and then we get the shuttle. We get some more experience, in spacewalking. And then Mir comes along. That's a Russian space station. And then International Space Station. We've done quite a few. Now it's completely built. So human history, this number is a little bit higher today. In human history, there's been just under 550 EVAs, or spacewalks, partners. And the mission to Mars, I had to change scales on us here, because that's just our first mission with humans. You pick the number. We're going to send either 4 or 6 people It's about 6 months, conventional propulsion, about 6 months to get to the surface of Mars. We're going to spend 600 days exploring, and then it takes about a year and a half to get home. 2 years round trip, orbital mechanics to get there, and probably your options are 30 days, 500 days, or 600 days. So I'm voting for the 600 days because this is a pretty expensive mission. So we need, it's a kind of game-changing technology, as we call this. It's an opportunity to provide maybe a completely new system, because the challenge is quite challenging. These are some images of this. I've been actually working on the BioSuit longer than before Incredibles came out, but I love the movie. Ours is not fireproof and not machine washable. It's polymers, and it's we haven't done that yet. We can put some Nomax over the clothes, if you will, and make it fireproof. So different concepts. So they'll tell you a little bit more about the design of the suit. Let's see. Okay. Oh, here's actually an illustration of the math. I'm going to show you the equations behind there, but this is actually important. So why does it look like a Spider-Man looking suit? I mean, aesthetically, it's beautiful. I work with a lot of designers, but it's all dictated by the math. It's three-dimensional eigenvector analysis for all of you guys who love math. And so what we do is we watch the human in motion. And essentially, if you drew circles all over your skin, and my students have, and I think one of my graduate students is painted at this moment. And so imagine you had little spheres all over your skin, and you moved, and you want maximum mobility and flexibility. Well, that, just like the illustration, my circle is going to turn elliptical, and I have two really interesting lines. So these intersecting bisectors, those red lines, guess what? They pivoted from a circle to an ellipse, but they didn't extend. So this pattern we actually call the lines of non-extension. So this spaghetti-looking thing is the lines of non-extension. That's fantastic. That tells us a lot. Now, this is where I need to put my wearable. This is why, back to the symposium and smart clothes. So if it's not extending, if I'm getting full motion, but I have a pattern, perhaps on my skin, that's not extending or minimally extending, that's great, because guess what? Then that's where I'm going to put my structure, if you will, or my sensors, or the things that I don't want to stretch. I want my elbow to stretch because I want to be doing good performance. So now we have this very interesting map. And so that's actually the part of the suit that we've patented to do this patterning or design to give you maximum mobility, but cause minimum energy expenditure against the suit. Again, the suit, I want to protect you, but I want you to be able to go do your work. So that's basically what's behind our design in the BioSuit. So Webb's work saying maybe we can use mechanical counterpressure, put the pressure directly on the skin, and then Iberol was the first. This is a very old image, and I want to reference Iberol thought about this idea first for the Navy, so it was classified. It got declassified in the 1970s, and then drew these. And then we came along, and I said, I think these are two great ideas. We tried to combine them, and then we just did the mathematical modeling and analysis. Well, we're continuing to do the analysis to see, is this biologically relevant? Is this really how skin collagen is laid down? I'm not sure. Maybe. But we'll keep working on it for another decade or two. I'm not sure we'll ever be able to prove that. But it's a very interesting theory. It's very interesting to think about the material properties and this patterning of skin. For an aerospace engineer, I know much too much about skin these days, but it's taken us down this very interesting path. A couple of the other things in technology and advances. This is work by colleagues, Paula Hammond and Greg Rutledge's lab at MIT. So we did a technology roadmap, and we came up with the 10 best technologies we needed to integrate into the BioSuit. And electrospinning was one on my list. Thought about in 1940, realized, researched, made progress, just recently, last 10 years. Now, is it commercially viable? Not quite yet. But the great thing about this was in Nature Materials, even a few years old now at this point, but now we can lay down polymers, if you will, in very interesting three-dimensional patterns, and that's exactly what I need. I need to specify which materials I want and in which orientation, and it would be nice if it was stable. Right now, it's not quite stable, these polymers, but you can, again, it's real designer materials, at a very high fidelity. So lay down the polymers, the materials that you want in the certain pattern that you want is the point here. So could we ever literally, spray on? These are just kind of evocative images but again, to get us thinking, creative, could we ever really spray on a spacesuit? I'm not sure, but this technology, electrospinning, spin lacing, comes about the closest in terms of what I know. So we do a completely digital design of the suit. call it the hybrid human now. So we go from the human form and put you in a laser scan or do motion capture, so I get a 3D image of you to the computer, then fabrication from the CAD models. We actually have to take our 3D models of you, if we were scanning you, we have to turn them into 2D CAD, because the best machines in the world, best sewing machines in the world still will take a 2D CAD image. We collaborate on just the production of these. These are just mock-ups. They kind of look and feel like, it's not an engineering prototype. That really applies the real pressure. So this is just a mock-up to show people the concept. But so Dainese, wonderful motorcycle, high-end athletic company in Italy are our partners here in terms of to fabricate some of our mock-ups. We're on about our 4th or maybe 5th version now. This is a size, it's my size, and it's 340 meters of the patterning. The black lines, a little unbelievable, huh? Yeah, that's 3 football fields. So it's pretty amazing. There's gold lines in here. The gold lines here are notionally where we would have some thermal control, again, our smart sensors, things like that. So we're maximizing mobility, minimizing energy, and we've made a lot of progress, but there's still something missing. We can get about 20 kilopascals, that's 20% of an atmosphere. I need 30%. So we've gotten a long way on just passive elastic, being creative about material selection, being creative about our design, but I'm at 20, I need to get to 30. And so we think that will really take some active material development. So that's what current PhD student Brad Holschuh is working with me on. So we've done now we're not material scientists either, so we talk to a lot of smart material scientists, we collaborate. Hey, what do you have out there? Because we have a spacesuit application. And the great thing is everybody loves our application. So we have wonderful collaborations and get a lot of help. So this is our shopping list. More recent, kind of our list of all the active materials that we looked at. And shape memory alloys came up on top, and dielectric elastomers were second. And so we worked those a little bit harder. And let me just see if this will jump to the website like we practiced. From Shapeshift, of course, we're on this is not our work, but show you some neat, again, kind of beautiful aesthetic work. I think I'll turn off the sound just to have nice music, but just to show you a little bit of this. We do like beautiful, flying, very elegant things. But these are dielectric elastomers. So again, I need flexible active materials because as far as I know, humans are very interesting, but we're three-dimensional and nothing is regular about our shape at all, and we're squishy and compliant, and you need a pretty interesting material to make clothes out of, especially when you're trying to keep someone alive in space. So I think this is going a little bit. So just a nice kind of capability. Looks like a kind of a morphing, flying wing. So we still haven't incorporated these there. It takes a lot of power. You see all these clips here and things like that. But you can control motion and flexibility and shapes. So they're pretty wonderful and nice. So we're paying attention to the materials developments here, and then the ones that we're working on ourselves in our lab are shape memory alloys. And you might know shape memory alloys. This is nickel titanium. And they're, let's just see. So just a little demo, biphasic. So a nice little cartoon character there, and you apply heat, and so you can have 2 phases. So why is that important? So for my suit, here's one of our little Chinese finger traps, if you will. So we have 2 shapes. I can have a compressed, so I can get more tension, and then I can have something out. So donning and doffing what sunk the earlier work. I need a bigger suit, I hop into, and now if it needs to shrink around me. So we're making progress. We don't have a whole suit, but it's not the whole suit. One of those images there was kind of like a knight of armor. I don't need an entirely smart suit. All I need is actually kind of, when we have questions and answers, or I can show this to people later, this is just stainless steel wire, but the idea I have here in this mock-up, so if we just push, had a little power source here, and I could just kind of zip myself up. And I can go from about 2 centimeters to nice and snug. So I can get, again, I'm only looking for about 5 to 10 extra kilopascals, and then I'll have the final pressure production we need. So, well, this paper will come out in 2014, so it's very new. And so we make our own coil nickel titanium shape memory alloys for, this is I think the best picture. We put the actuators there. So just imagine this is around your arm, and then we're just going to cinch it up. And it has very interesting shear stress characteristics. Again, biphasic, so we kind of take advantage of going up and down those curves, if you will. I brought our current helmet. This is a new helmet design that we have. Again, just conceptual. What's different about it? When you see most spacesuits, you see a big. Early on in Gemini, we had a smaller helmet. Then we went to a big spherical helmet in Apollo era program, and we've kind of kept with a spherical bubble helmet. And so you can look around in it. Your field of view is okay, but since I like tight-fitting, close, use the human body for what the human body is, we've made a much more conformal helmet. It's a little clamshell, so you kind of hop in that way. You put it in. Now I'm going to rely on my neck musculature. So as I look around, the helmet moves with me, and I can see. And we have a little mock-up of it there. We do actually put a little Google Glass in here. Students can come up and talk to me about these. I'm a novice user of the Google Glass. So far, I can take pictures and things like that. I can't run our code yet, is the problem. But this is really important because we really envision quite the smarts of the suit, if you will. The smarts of the suit are pretty much you're wearing them. We want the IT architecture for the suit, and I'll show you kind of following on that what we envision and what we work on. This is kind of the day in the life of my Martian explorer. This is a program. We develop path planning, mission planning tools. So it's called Sextant. So appreciate that. And we load in, these are digital elevation maps. That's actually the Atacama Desert, because the highest, driest desert in Chile is a really Mars-like place. And so it's fantastic. We were there in last May. So again, very volcanic, great place to look for space science, planetary science as well as exploration. And anyhow, it's red, those peaks are red because I'm dialing in a slope, maximum slope, 20 degrees. So people can go up and down even more than 20 degree slope. Vehicles are not very good at all. They can go about 10 degrees up or down, and then you might lose your rover in a crater. And then what we do is we plot, I send my astronaut out here on the blue line. I send, my robots and rovers here, and, we're exploring to see, because again, we think this is actually what it's going to be like when people are with the rovers and robots on Mars coming up. And we're doing calculations and, again, putting weights, things like that. And what comes out of it is the energetics. How much oxygen do you need to do these kilometers, tens of kilometers of rails? When should I be riding my rover? When can I walk? And then if there's an emergency, we always calculate something called an emergency walk back time. It's actually going to become more of a very fast running or loping if you have those kind of emergencies. So we do those kind of calculations, plan the path, and go out in the field and test these out. Just as we've been really fortunate to get a lot of PR, because I guess we have a great aesthetic-looking suit. But the reason I include this is, to my surprise, to my wonderful surprise, the kids around the world, and particularly the young girls that come up to me now and say, I want to be a spacesuit designer. I mean, that's what makes it all worth it, right? Because I have little kids, and now girls and boys, and because they think, they could do something like this, and they could design one of these. And so I'm recruiting them all. I need all of the youngsters that we can to solve a lot of these tough problems. And then I think this is getting to my last, just for interest, I thought you might want to see this is our shopping list of kind of the breakthrough technologies that we're interested in, that we're working on. We kind of call it superhuman performance. Is that reconfigurable hybrid humans? This hybrid humans, Hugh Hare, a colleague of mine at MIT, and myself, it's very easy to imagine a world without disability, only ability. So what can we do with a human and machines in parallel to walk as fast as you want to walk, run as fast as you want to run? The athletic performance, of course, is you can maybe make superhumans, but just helping people here on Earth locomote just to get maybe more mobility if they don't have it is something we're very interested in. And so those are augmentation technologies, again, for balance, strength, states. So exoskeletons, there's still a lot of work in exoskeletons. I just look at my BioSuit as a soft exoskeleton. And so we've worked on the sensing part, the tracking part. We can sense the limbs in motion. The next really hard challenge is the actuation piece. Because if I can't move it with my own muscles, then can we help someone move? And so can the suit on board and a wearable technology, can it help you move your limb however you want to move your limb? We'll have to talk. We'll have to talk about that Polynesian boat. It's actually in Honduras. But my last slide is this one. I'm going to take you on a trip. This is filmed very recently from the International Space Station, and this is what the Earth looks like. It's sped up. Turn down the music a little bit. It's very nice music. It's legal to use it. Peter Gabriel donated. It's a very beautiful song about gravity. So we're flying over the US. It takes 90 minutes for the space station to orbit the entire world. It took us a year and a half on our boat. They get to do it every 90 minutes. The atmosphere is right there. It goes on. It's very lovely. You can download these from YouTube. A few things I'll point out. You can definitely see where the energy is being used in the lights on Earth. The atmosphere, the space station is not very far up. It's only 400 kilometers. We're a couple hundred miles up. So if I shrink the Earth down to a basketball, our entire life support system, our entire atmosphere is 3 human hairs on the size. So you're looking at the atmosphere here. So that's how fragile and wonderful. And I want to leave with the comments there and go full circle to my image from Buckminster Fuller, and kind of the inspiration to say, and I'm fascinated about space exploration, but again, and what we learn from all of our space work just helps us kind of reflect here on Earth, and maybe gives us a different vantage point on how to solve problems. So thanks for your attention. I'll be happy to answer questions.
So thank you, David. That was amazing. So for questions, I suggest you raise your hand, and Paul back there has a portable mic, since we are capturing this for, I guess, on video. So if you have a question,
Thanks
please
for
address
a
it.
fascinating talk.
Thank you.
I wonder, when you're designing these suits, how do you protect the skin of the astronauts, which must continue to function like skin, and if it's going to do that for 2 years or however long?
Yeah, we put on in current systems, or even in our system, you put on just an undergarment. It's not too different than dressing up to go skiing. Put on we want a nice low friction undergarment, but not too much special to protect skin. I mentioned the injury. I was talking about shoulder injury, things like that, but a fingernail injury is probably the worst problem in the current suit. So there's actually a few astronauts who take this to extremes before their missions. They actually remove all of their fingernails. That hurts. It also hurts when you lose them after the flight, so that's pretty extreme. Maybe I'd recommend a little moleskin, a little low friction in your gloves, but when you're there working and your job is to fix Hubble, you're going to fix Hubble. And this is tough. This is really tough to work against a pressurized glove. That's why we think it makes much more sense to kind of put it directly on the skin. The number of degrees of freedom I have in my hand is more than my whole entire body. So this problem is probably as complicated as the entire rest of the suit. So it's a good problem. But so not too much extra special though for skin, except for that. Again, as an aerospace engineer, it's marvelous. I'm in awe of the designer because it's one of our incredible organs, and skin is really amazing. They got all the material properties right and everything else about it. So I'm just, always in awe of the natural design. Feet hurt too in space. Fingers, I just should mention, and feet. Why do feet hurt? Well, when you get in the suit, the current suit, again, it's kind of like having shrinkles, right? Because there's a bladder in there to keep the pressure in. So you hop in your suit, you're getting these boots. Remember those Scott ski boots? They really hurt, right? I still ski today with very painful ski boots, right? You can imagine getting in your spacesuit, and if it kind of wrinkles up that bladder layer, you're going to be out there working for 6 hours. So, and then also, since we're floating around in microgravity on station, the top of your feet it's really soft. It's really nice, soft skin. So you'll be in a foot restraint, but I might be working. So I'm in a foot restraint, but I'm here all day. And I'm coming up again. So all astronauts all come back with calluses on the top of their feet. But that's a small price to pay.
Thank you for the talk. It's very inspiring. I actually have 2 questions.
Sure.
So in the very beginning, you talk about you are now your team looking at the tunable stiffness. Mm-hmm. Could you explain what's the scenario when the tunable stiffness is usable? Great. And the second question is, you explained that you are looking at the shape memory alloy and the EAP as the actuation method. Have you also considered pneumatic as actuation?
Okay, great. So all is good. So help me remind. Okay, so yes, and so for the first question you wondered about was the tunable stiffness. So that's about our best idea that we're working. So when we did the first one of those exoskeleton videos I showed you, we stiffened it up. And we said, okay, if we want to simulate a spacesuit, we need to stiffen up, and then we'll figure out how you're working against this stiffness, how much energy penalty there is. But then when you get to the moon and you're in 1/6 G, or in a gravity field, 3/8 G of Mars, maybe you don't always want maximum mobility. I spent 20 years thinking, oh, maximum mobility, this type. But if I'm actually there, doing some geology or rock sample, maybe I don't want to have to use my own musculature, so maybe I just crank up the stiffness in my knee joints. So it's like now I can sit against my suit. So this gave us the idea of a variable stiffness suit. So mostly a lot of flexibility, but then if you could just dial in, stiff joints, so we play around with that. So that's where the tunable stiffness idea comes in. Use it to whatever task you're doing. And then you asked me about some of the active materials work that we're looking at. And the shape,
I was asking, have you considered the pneumatic?
So we did, we were working on that for a while. In terms of a spacesuit simulator is where I use pneumatics. Again, I have that robot. That's a hydraulic robot, but of course you can get great force, torque characteristics out of it. And so we finished up and developed pneumatically. Actually, we use McKibben actuators, if you know the field, to do basically antagonist, protagonist pairs, muscle pairs, if you will, to move. The thing is, it's an exoskeleton. It's very massive. I'm tied to my compressor. My pneumatic compressor is right there, so I don't really get to go out of the lab. So pneumatic systems, I like them. We've developed exoskeletons with them, but they're not very wearable and portable. And so that's the issue we run into. They give us really great force capabilities. That might not be obvious to everybody. Humans we're strong, we're tough. So trying to get something that replicates a muscle, your bicep muscle or tricep pair, that's quite a lot of torque. And so you need to go to hydraulics, and pneumatics can match that. And the only other thing that we've seen that can match it is actually the shape memory alloys and some interesting shape, and these coil, these kind of interesting design shape memory alloys, because there's a lot of other great stuff there. The little flying birds, all those are below what I say is the human force torque characteristic level. Piezoelectrics, piezoceramics, all these they're great, they make great little ants to go searching on Mars, but they're not big or tough enough or strong enough, I guess, to scale up for the astronaut performance. Sure, thanks for the questions.
Okay.
Hi.
Oh, well, wait, can you wait for the microphone?
We'll get you a mic.
Yeah.
I can hear you, but they can't.
Is it possible to send robots into the space and do all the work instead of astronauts? And how difficult is it? Mm-hmm.
So it's possible to send... Yeah, so the question is it possible to send robots into space to do all the work and replace my humans? So it's a great question. And so we have a lot of rovers and robots in space right now. That's the great thing. You know how many rovers and robots we have at Mars? Lots. We have a lot of great things happening on Mars right now. We have people living in space station. That was my image. But we have Spirit and Opportunity, and we have something called the Mars Science Lab. It's fantastic. And all those are either orbiting Mars or on Mars today. They're pretty slow. The Mars Science Laboratory that's there now has really good cameras. So we actually know more about Mars and the moon from our images and from the robots and rovers than we do about most of the underwater world, our underwater oceans on Earth. So we do go with rovers and robots. We still haven't found any past evidence of life on Mars, and that's our scientific question. And so it's going to be humans and robots together. It's always humans and robots together. But robots on their own, they're great. And you can put in a whole bunch of autonomy. There's always usually a human involved somewhere. Like I might be back at my desk, I might be back at mission control, but usually there's a human helping the robot, if you will, in that case. So to me, it's just a matter of where the human's located. The humans, we might stay on Earth, maybe we go to space station, maybe we operate. So we're always going to be working with our robots. And the robots have, the space robots are really quite limited. So I can't wait until they get better. But right now, I'm faster and smarter and more flexible. And so right now, the humans have an edge over the robots. But we're trying to get as much exploration done because they're a lot cheaper and maybe it's safer. So there's good reasons to send both. But when you send both humans and robots, you get a huge benefit in terms of, say, information, understanding, scientific return. Does that make sense? So they're always going to be working together. To me, it's just kind of location. Who's on what surface?
Hi, thank you for a great talk. I have a question about how do you design into the material safety against rips or punctures? Is there new ideas of how to deal with that?
About safety and rips. Thanks. There was a bullet there that I had on safety. And so in a conventional design, a gas pressurized shell, if you're in a balloon and you get any kind of puncture, we're talking major emergency. Game's over. We do have 30 minutes of emergency oxygen that you can breathe, but you're going right back to your safe haven. If it's, Station or, we can talk about Gravity later if you've seen the Gravity movie. Those things all can happen. They don't all happen at the same time. And it's, they missed the physics. I liked it visually. But anyhow, back to what happens. So if you get a micrometeorite hit or just anything, if you wear and tear, you might use your hands so much that it's like a good pair of Levi's, right? Like really good old Levi's to move in. Well, you like really good old gloves too to work in. You can only wear them so old when you go into space. But I want the beat up ones that I can really move my hand in. Maybe that palm bar might wear through. We've had a couple instances of palm bars wearing through. You need to get back in. You need to get back inside. The BioSuit, it's actually, that's a huge advantage actually of our design, a safety advantage, up to, a millimeter by millimeter. Small, if I get a small little tear, puncture, I'm on the moon, the regolith, that's just lunar dirt, it's really sharp, and it might poke me and something like that. No problem. You'd put another layer. It's like a smart ace bandage is how I like to describe it. Just wrap yourself up. Now you can't have a gaping hole. I don't get to, my whole suit can't come apart, right? But if you have something small, you just keep going about your business. So that's because we're not trapping air in the suit. So we just need to apply pressure. So we have a very large safety benefit, if you will, from the conventional technology.
Quick question. So thank you. So your target for your suit right now for the pressure is 1/3 atmosphere.
Right.
And I'm wondering how comfortable that is for human beings and what the long-term effects are.
How comfortable and what?
What the long-term effects are.
Oh, what the long-term effects are. So it's really comfortable. We're at 1 atmosphere right now, and we're all pretty darn comfortable. So you can sustain. Now, here's the problem in my lab because, this is going to give you a 10%. A 10th, because that's how we design our mock-ups. So if you're in the lab, and we're at 1 atmosphere, and I want to put a third extra, 1.3, on you, I'm overpressurizing you. So that's not too comfortable. And then you hop in the vacuum chamber, and we have a small vacuum chamber in my lab, so it's for arms and legs. So you wrap up the leg, you hop in, and then you're in the vacuum chamber, and then it's really 1/3, and it's fantastic. So it's low pressure. It's actually a low pressure environment, so it's very comfortable. The second part of your question, though, I want to speak to because long-term effects. Can we? Right now, the current suit, again, is heavy and bulky. You can wear it 6 hours, 7 hours. We've set records. 8 when things don't go right out there. You wear it for 8 hours. You try to get the satellite or whatever you're fixing fixed. So 8 hours is, and also the life support system is about as long as we wear current suits. So that's what we're designing for as well. Actually, 4 to 8 hours because when we're on a planetary surface. It only makes, we need a light, fast, rapid system. So we designed small oxygen tanks for the life support system, move around. I'd like you to go out in the morning, do your work, come in, maybe eat lunch, go back out in the afternoon. And that just makes sense from a modularity type of design.
Radiation is also one of the problems that obviously we have to face, and it's one of the biggest problems.
Yeah.
So in terms of radiation, what are you working on to protect human beings from?
Yeah, so you're absolutely right. So if people ask me what the showstoppers are for sending humans to Mars, radiation is probably number 1. Musculoskeletal, the skeletal system, which is what I work on more, is number 2. 2 and 3, and then I would say the human factors, the psychosocial. Because you don't want, you're in a very small canister with 4 friends and you don't want to kill each other. So there's real psychosocial human factors issues. So those are the 3 showstoppers. Cardiovascular, all the rest of the systems, I think we have pretty good solutions for, but this 4-year Mars mission. So we don't intend to put much radiation protection embedded in the suit because it's massive, it's dense. But on the way to Mars, going to Mars, one of the best radiation shields is water. That's great because we like to drink water. So just in terms of a design, so we do a lot of systems architecture and design. So you need the water to drink or you're going to make water just like on a sailboat. And so if you put that in the walls, you have pretty nice radiation protection. When you get to the surface, the moon has been studied a little bit more than Mars. There's some great lava tubes. So they're more like radiation shelters. The Apollo astronauts, not so many people know, the Apollo astronauts were very close, days away from a major solar event. That would not have been good. They got normal radiation, so we really pay attention. Of course, now we know, and so the current rovers, the current robots on Mars, that's exactly what they're studying, environmental radiation. So once we can map it, once we know it, to much greater resolution, we'll figure out how we do have to protect against radiation. But it's much more the vehicles, the systems, whatever I'm wearing on my back might help, but probably not in the suit, because then I lose all my mobility and lightness.
So at the moment, sorry, so the vehicle itself is also a problem. The suit is like follow-up vehicle. We don't have a vehicle to send people to Mars yet.
Oh, no, we don't, unfortunately. Not even to the moon, to my chagrin. But people are working on it. Hopefully, we're kind of stuck in low Earth orbit now. But I don't think it's going to be too long before we get to leave low Earth orbit for humans.
Do you already have your questions answered?
If I can, yeah. While you're asking, there will be people on the moon for sure within the decade. China's long-term space plans are to be at the moon by 2020, and India is also very interested and sending. So China and India are in this very interesting kind of space race. U.S. and Soviet Union have kind of already been there, and so we're interested in the moon, but we probably more have our sights on Mars. So it's all now it's human will. Where do we want to go, and we want to go together. Because there's probably the knowledge, and I'm not sure if we muster the will to probably go together. I think humans could, but I think it'll be a global mission to either the moon or Mars within the decade. A human Mars mission is further out, decades out. But a human moon mission, we did it quite a long time ago in 10 years, so that's very achievable. It only takes 3 days to get to the moon, so.
Yeah, thank you. Very, very interesting stuff. I have a question. In the current NASA suit, you're applying like hydrostatic pressure, so the pressure is relatively immune to the volume change of the individual. But when you're breathing or with different hydration or things like that, how do you deal with the
that for
creature
both
changing
suits?
volume, short term and long term? Yeah, for where you're applying pressure on the surface.
Right. So, well, first let's back up to the current state of the art. The current suit, we try our best. Again, great engineering. It's called a constant volume. It's a balloon, but even that, you're moving your arm and things like that. So they really pay attention to details about restraints and things. So even when we're in the current suit, we're moving. We want to keep it as constant volume as possible. Do a pretty good job. And you say we have a volume of reserves around us, so you can kind of move and all stay within that life support system. So for the BioSuit, we pay a lot of attention to that. So we measure that at great detail. I want to get to 30 kilopascals. Again, we measure 20 to 25 at our current state of the art. And so we take measurements, pressure measurements all over the body. How am I applying pressure here, pressure here? Arms and legs, they're pretty good. Concavities, not so easy, right? The back of your knee, your armpit, these are harder parts. We'll probably, interestingly enough, we've done a lot of, physiological testing, edema testing, things like this. How's the person doing? It surprised me. We can easily withstand plus or minus 5 kilopascals, and we don't see any adverse physiological effects. But the idea is still constant pressure.
Is breathing easy though?
Is breathing easy? So again, what you don't see, we have some concepts, well, more than that, some engineering analysis, because I have you in this helmet, so I have to provide the air, a really nice seal, but where does all that air go? So we have, basically on your chest, you have a pressure compensator, and it's, it looks like one of those old-fashioned water, those bladders, hot water bladders. Yeah, I kind of have that in the chest. A bit of a concavity, of course, in the chest, and so, I don't know the exact volume, like this, and breathe in and out. And of course, then the mechanical crown or chute on the outside. But yeah, it's not, again, a third of an atmosphere is really not bad at all. So it's actually, these are easy to achieve. Just like medical applications for compression stockings or hose you might wear, it's well under 10% of an atmosphere. And just, normal stitching and materials can easily do that 10% of an atmosphere. We only need 30% of an atmosphere. So it's still a low pressure environment, so it's not too tough. The medical applications are even easier.
Thank you. I'm wondering if there are any advantages of a gas pressurized suit over the contact pressure suit, and whether you can, if you can make a skin-fitting suit that's also gas pressurized.
So first question, so are there any advantages of a current, conventional gas? It's, I guess the big advantage is it's the only system that's ever been flight tested. It's the only thing we've ever done to fly in space and test it, so we have a lot of experience with them. A lot in both in the Russian program and the US program, and now the Chinese have a little Russian suit. So it's a small suit, but it has it's pretty similar technology to the Russian suit. So, NASA, the US, China, Russia now have suits. They're all, they're actually very different materials. The Russian and Chinese suit have very similar materials. They're really interesting. It's a lot more cotton and leather. Actually, the Russian suit has leather soles. I couldn't believe, like my boots, so there's leather soles. It's fantastic. I loved it the first time I got in the Russian suit. We use things I can't pronounce, Kevlar impregnated polyurethane, again, just to try to, mostly you see a suit is white. That's just the outside of the suit. That's for micrometeorite protection, and it's really nice to kind of impregnate that with Kevlar. But there's bladders, there's a whole bunch of what's called aluminized mylar inside. It's like fancy aluminum foil. So there's layers and layers. So that's another disadvantage of the current suit. You're in a balloon, but now it's a multi-layer suit. So, but again, a huge advantage that we know the system. We've been working on it for decades, so it's proven and tried. And I should be able to try to think of a few more advantages, because I spent my life thinking about mobility and lightweight and flexibility. So would you ever put gas in, would we ever try to enclose gas in there? No. That would actually be really hard and it would defeat the purpose. The purpose is to get rid of the gas. But in actuality, if our research helps inform NASA and we go with a hybrid suit, I'll be happy. I can retire as soon as NASA incorporates, some of our design ideas. So I think a hybrid suit makes a lot. Again, in some sense, we already have a hybrid suit. I'm showing you a gas pressurized helmet. That makes sense. We've probably all seen the Blue Man Group. I love the Blue Man Group, but there's no reason to shrink wrap an astronaut's face. I mean, this is a difficult thing to do. I don't know, I guess they do that with blue paint, right? But that doesn't make sense. So it doesn't make sense for me to shrink your face. I'm perfectly happy with the gas pressure. So I kind of think more of, again, more of a hybrid. I think a hybrid really makes sense, especially moving forward.
Hi, thanks.
Hi.
Yeah, I don't want to take any time from people who are asking about your specialty, but since you mentioned the psychosocial factors, I remembered a couple of years ago, there was a talk or an interview on NPR, I believe, about sending young people to Mars to colonize with no intention of bringing them back. And it made me worry very much because young people, they might not know what they're getting into. And I mean, I came here to study from a different country, and I know how hard that was.
Yeah, a big trip.
So anyway, so if all the other
questions
are finished, if you
I'm
like
glad
to
to
speak
take
on
that.
the
So,
psychosocial.
why explore? Why send humans? These are great questions.
No.
But young people,
I'm all for exploring and sending humans.
No one's going to send young people on a one-way trip to Mars. Matter of fact, we're not even going to send old people on a one-way trip to Mars. Right now, because spaceflight, especially exploration, is being funded by world governments. It's not in any policy statement to send people on a one-way trip. Now there are plenty of volunteers. We have a lot of volunteers, so that's a different issue. But NASA, and I can't imagine any other government, we're going to do it round trip. Round trip's harder because of the fuel. It's mostly about propulsion and fuel. You have to get the people home. So what makes really good sense is to send your fuel out there ahead of time. Mars is an interesting place because we can make methane propulsion. We need really good robots, but go out there. It's been demonstrated in technology. So you kind of it'd be really nice to have your fuel depot there. Now you send your humans, and you only have that propulsion to get there. Do your exploration. It'd be really nice to have the gas to come home, so you have your propulsion system coming home. But everyone's only talking about a round trip for the early explorers. But how many people perished in Antarctica and the Arctic? So we will probably lose life. That's what exploration is all about. But the volunteers that want to do a one-way trip, I can't imagine anyone funding that. There's an interesting, crazy idea you've probably heard about, Inspiration Mars, to send a couple in 2018. so that's just right around the corner. And they sent a couple on a Mars flyby. Now, they don't get to go to Mars, they're only going to see Mars for about 12 hours. It's a long journey, so put two people, that's a commercial idea, it's a commercial program. We'll see if it reaches fruition by Dennis Tito and then some other folks, and I hope they need a lot of technology development. It's a great idea, Inspiration Mars. I mean, I love the name because it will inspire the next generation. There are a lot of serious safety concerns. And again, that'll be a flyby of Mars. Again, Mars is very far away. So if you go to Mars, it's much easier to do basically a figure 8 orbit, and so you could wave to Mars, but again, you're going to see Mars maximum for a few hours. It's a long trip out and a long trip back, and we wouldn't be doing much science. You could take a lot of photographs, I guess, but that's we'll see what happens. There might be a breakthrough moment, perhaps in exploration. It's happened, previously hundreds of years ago via sea, and so we'll stay tuned. But the world governments were, decades probably from sending humans.
Can I ask you a question? Thank you for your talk, by the way.
Sure.
I'm wondering, you've spent a lot of time and you're clearly passionate about this topic, and I'm trying to think of an analogy of what it must be like to then not go out into Mars and test it. Is it, kind of like a cook who bakes a perfect cake and then can never taste it? What's it like for you professionally to be really, really perfecting this?
It's my real job is to teach and inspire young people, and so as long as I do that, I have a great story to inspire folks and hopefully teach them the science and engineering, math. I turned it from STEM to STEAM though, because I think I get everybody if I include the arts, and I need everybody because again we have some tough problems. So that's my job. So I've admitted that I personally am not going to go to Mars. But I really hope one of my students, I'm not giving up on the dream. I really hope, one of my students or colleagues or, the next generation or the next generation. So like I said, I would probably dedicate, another 10 or 20 years of my life to getting people there. We're on a little bit of a glacial pace now. I'm waiting for, there might be a breakthrough mission or technology or something like that. And if, my young lady left, but if the rovers or robots find the evidence of past life on Mars before get humans there, fantastic. Then maybe you don't send humans in. Then you get on the moons of Jupiter and Saturn are really interesting places. So those are they're really far away. Would you send humans? I'm not sure. Teleoperation, for sure. We're going to send rovers and robots. We know we send probes now. But there's a really interesting places in our solar system to do exploration. So I'll keep working at it. It's hard that every space station mission, takes me about a decade. So we have a lot of fun with, of course I am an academic. And so you studied, you have an N of 4 and it took you 10 years, so you get to study 4 people and spend a decade of your life and then publish that paper. And they say, no, go back and do it again. Say, no, you don't understand. We don't get to do this again.
I would phrase it thus: you're one of the giants on whose shoulders they will stand.
We hope, thank you. Yeah, we all stand on the shoulders of the others. So I'll keep the dream alive for sure.
Hi, thanks a lot. I wanted to ask about if you could elaborate a bit on the variable stiffness and if it's zoned in different areas, and if it could actually, if you were injured, maybe stiffen a cast or whatever.
Exactly. Yeah. So So it's very so it's specifically to the joints. Absolutely. The only thing we need to probably have mobile and then is different degrees of freedom. The elbow is a nice simple joint because it's kind of called this a 1 degree of freedom joint. Shoulder, pretty difficult. This is a complicated ball and socket joint. So this is more complicated because every motion I do, I need a lot of, so do I want to stiffen it in this direction, abduction, this direction. So we have a lot of choices in the designs and how to stiffen things again. So it's very important because of course, it just is the normal aging process. I'm stiffening up as I go, and both the muscles and the joints. And so sometimes you want stiffness, sometimes you want less stiffness. So just being able to dial that in, we think is really important for our designs.
And is there a number of zones? Is that how,
zones? It's just joints, just joints. Yeah, just shoulders, like the robot that I have, 12 degree of freedom robot. So we're looking at that. But yeah, just joints. So going from wrists to elbows to shoulders, and legs would be the same. You definitely need a waist bearing And if you look at the biomechanics elements of gait, I learned this from Tom McMahon, my former mentor, wonderful mentor I had from Harvard. And you break it down. If you want someone to walk naturally on the moon or Mars, then for sure you're going to put in all the elements of gait. And two really important ones are pelvic tilt and pelvic rotation. So pelvic rotation and pelvic tilt, because as we walk, that's exactly what our hips are doing. And if you don't design that into it, now here, I don't have a problem. I get all those degrees of freedom for free. If you have a big pressurized shell and you don't give someone a waist joint, now that's why they're not locomotion suits that you see, the bloopers, and they didn't have that mobility in the Apollo suits. So those were too stiff. So we don't want it too stiff, but on the other hand, you probably don't want it too limp when you want, the advantage, I just thought of another advantage to a gas pressurized suit. If I'm on the moon or Mars, it self-stiffens, right? Because the balloon, so those legs and those arms, they fill up and they self-stiffen. Sometimes that's a good thing, because then I can just have my muscles say, okay, relax. The suit's holding me up. So that's actually another advantage, talking about the stiffening and what properties we get out of the suit. Does that help answer your question?
I think we have time for one more question, so.
How do you manage temperature?
Sorry, I didn't hear.
How do you manage temperature?
How do you manage temperature? Thank you. Two ways. So this, just again, notionally, there's a lot of little gold lines in here. They just follow the black lines. But the reason that we have them in there is that's a really great way to manage about plus or minus 10 Cs. So thermal comfort. You know, crank it up, crank it down. It depends on, well, it depends where you are, and it depends on the heat. I mean, Mars is a cold, dead place as far as we know. It's freezing, barely, or always below freezing. Right now in low Earth orbit, you can get plus or minus 200 Cs, right? 180 degrees C, it can be very, very hot. It can be very cold. The moon, same thing. Are you on the dark side of the moon? So depending on where you're at, we have huge temperatures that we have to protect against. So this just gets me comfort and control. And then you put that in the outer garment. So again, that's why spacesuits are white, because the real thermal control system is on the outside of the suit. And right now, the current technology is a lot of aluminized mylar and then that big white outer shell. And that's for thermal comfort and control. It's protecting you from the environment. Basically, it's keeping your heat in, not letting it escape. On the other hand, from the heat coming in, it's protecting you. So it goes both ways, because we have huge temperature fluxes. So what we think, two answers, so right there on your skin, again, that's just a little bit up or down for comfort. And then just as we do Antarctic exploration, you put on your overcoat, ski clothes. They're pretty darn good for, my sleeping bag, I think, does actually go probably, at least 100, Fahrenheit or Celsius, whatever we want to talk in. Does that make sense? But yeah, so we decouple it from the mobility, pressure production. This is really the pressure production layer, and we decouple that from the temperature and some of the other thermal controls. But it's very, very important. But it's not a huge technological challenge.
So let's thank Dava again for a wonderful talk.
Thank you.
And thank you for coming.
Thank you.